Thanks everyone for joining. My name is Shawn Tabrizi. I'm one of the developers working on Polkadot, and I'm here to talk about shared security. I'm here on behalf of obviously Polkadot, but also the Polkadot Blockchain Academy. The Polkadot Blockchain Academy is probably one of the most, in-depth courses and programs we have in the entire blockchain space about educating not only about Polkadot, but about blockchain in general. We go over tons of different topics ranging from game theory, economics, cryptography itself, all the way to blockchain development, smart contract development, and of course, Polkadot itself. I'll be going into one of the lectures I present during the Polkadot Blockchain Academy, which is about shared security and kind of how Polkadot achieves the scale that we have delivered so far. But before I go into that lecture, I wanted to give a small preamble to kind of give a little bit of insight about the latest thinking and kind of frame the shared security talk into kind of how that maps not only to Polkadot's present, but also its future. So that will be the beginning here, this preamble, shared security Redux, an updated view into the vision of Polkadot. And of course, if there's any questions, feel free to pause me, ask. I'm happy to answer, and we can take this conversation in any direction you want. Okay? So I think it's really important right now to just remind people that the blockchain space is kind of weird right now. There is a growing divide happening in the blockchain ecosystem. I think we're seeing a lot of people thinking about long-term thinking, about like how we're actually going to build and design systems which will last for centuries, generations. And a lot of short-term thinking, people who are literally trying to build products that will win the market tomorrow, that will kind of make compromises, do things fast, break things, and try to deliver something that happens out there. And I think one of the things that kind of stood out to me was when I was at a DevCon in Thailand, and there was an announcement or presentation around like a 5-year roadmap for Ethereum. You heard one side of the audience being super excited about this, really powerful, decentralized, scalable future for Ethereum. And then you had another side saying, wow, 5 years, they're going to die before that. It was really bearish and very nasty. And I think this is kind of gross. I think that, we shouldn't be looking to build things with short-term results. We should be thinking about how we can actually design things for the long term, right? So I think I want to remind ourselves, before we even get into any conversation, about the original Web3 vision, right? Web3 is all about a world with less trust and more truth. And when we talk about Web3, we're talking about all these different properties, right? Systems which are decentralized, verifiable, self-sovereign, interoperable, privacy-preserving, open, public, borderless. You can read the list, right? And I want to clarify that, there's a lot of people building things in blockchain. And I think that every Web3 system will probably have a blockchain somewhere in there because blockchain provides a lot of these properties. But not every blockchain is Web3. There are many blockchain systems out there which are trying to, basically ride this wave of excitement and money and try to sell you something which is not much better than the existing systems that are out there already, right? So I think it's really important to remind ourselves what kind of system we're trying to build and to not be fooled by systems that will try to use this word, use this technology, and pretend to be something that they're not. So what was the original Polkadot thesis? Polkadot has been being developed since 2016. Really parachains launched back in like 2021. It's been a long time we've been actually building this stuff. So the original thesis was, how can we scale blockchains without compromising these Web3 principles, right? And if we break down the white paper, it really was down to like 5 bullet points. It wasn't exactly these words, but these words kind of developed over time. The words are shared economic security, application-specific chains, execution and data sharding, native rollups, native interoperability. This is really the basis of what we thought would make a good blockchain protocol. And it's pretty much what Polkadot has delivered. And I think if you look at what's happening more recently, you would see we made some pretty good decisions, because you can see that Cosmos figured out, hey, shared security would be a great idea in 2023, many years after we talked about it ourselves. That things like OP Stack said, hey, application-specific chains would actually be a really good idea too. We already built Substrate. They started introducing OP Stack. These are, ideas that kind of resonate. That things like Near finally implemented things like sharding, data sharding, right, and execution sharding. So it's really nice that, after so many years, they also came along the ride with this idea as well. And finally, that Ethereum itself is finally really putting emphasis on native rollups and interoperability, right? This is the latest kind of report from Justin, January 2025. So this is just happening right now. And again, as I mentioned, the white paper from Polkadot was written with all these same ideas in 2016. So I think we were on the right track, right? Yeah. Now, I want to clarify, there's no monopoly on these ideas. It's, we built some systems out there, like, whether or not Polkadot was as successful as it could have been or whatever, who knows? There is no monopoly on these ideas. But I do think we have gained a lot of insight based on the fact that we built these things first, and we've learned a lot from implementing the system. Like, the things we describe exist today in Polkadot, right? People are still trying to build it, but we've already learned from what we've built what we can build better. And so I want to give some of those insights in this prelude. So first, I think we need to reevaluate our previous assumption. The previous assumption in Polkadot was kind of like application-specific chains. But we should ask, do applications really need their own blockchain? Is that a fundamental assumption that we should make in this system? Well, I think applications do need their own blockchains right now because existing platforms are not flexible enough, right? Web3 applications, they want that decentralized consensus. They want the properties of blockchain, but you can only secure certain kinds of apps on a blockchain itself, right? And that's like smart contracts and blockchain rollups. Well, why is that? Well, smart contracts are kind of special programs that are designed to run on a blockchain. So a blockchain is itself split up into multiple different blocks, right? Where you execute piecewise some kind of transaction or execution or block, and it needs to be able to execute all those things within a small window. That's what the blocks are, right? Smart contracts are basically designed to be applications which run piecewise. They run small chunks at a time, update the state, and allow other people to then access it, right? But the problem for many application developers out there was that traditional smart contract platforms or traditional smart contracts were not flexible or scalable enough for building full Web3 applications, right? So that's why many of them now switched to building their own blockchains and then using blockchain rollups as a method for securing their chain. So, of course, you can also secure another blockchain on a blockchain because another blockchain is itself split up into separate chunks, which you can then execute and verify and come to consensus with on another blockchain. So this was kind of the more flexible approach to how can I control my own blockchain, but then have it gain security from another blockchain, right? Now, I want to clarify, like, both of these systems basically are very specialized. Like, if you want to build smart contracts, you're building applications in a way that's not normal for a normal application developer. You have to learn a whole new vertical of technology. Same with building a blockchain. A blockchain system is completely different than the normal kind of applications you expect or you understand from the Web 2 world or before that, right? So this creates yet another barrier for achieving, the world that we want to achieve, the world with less trust and more truth. So I want to kind of identify an old paradigm. So if you're building an application today in the blockchain space and you want these Web3 properties, you basically had to have an application which itself was split up into small chunks which could fit into blocks, right? But the better solution, and this is basically saying that all application developers need to build their own blockchain. But the better solution, I think that we would really want to do, is have an application that you could just build just like any other application, using any framework you want, right? For any kind of computer, and just have it run on a system which itself provides those Web3 properties, those resilience, decentralization, and verifiability, right? And so kind of the direction Polkadot is, I believe, going towards is this idea of a Polkadot cloud, where you can just build an application without knowing there's a blockchain underneath, and we'll take care of the rest of the work to be able to actually run these things in a blockchain. Again, you as an application developer do not need to think about building for a blockchain. You just think about building your application, and we can provide to you the properties that blockchains the blockchains will provide for a Web3 system. So the future of Polkadot, I think we've already built, and we already exist today, a platform for securing blockchain rollups. That's already done. Now we're building a platform for securing any kind of application. And I think that's the direction and the future that we're going to be going towards. And this is powered by evolution and innovation. And evolution using our existing knowledge, existing technology stack, and making it better. That is things like multi-core execution, elastic scaling, and pay-as-you-go. But also innovation. There are new things that were just introduced, new technologies like JAM, which is a new protocol for decentralized computer, and the PVM, a new kind of VM, which allows you, which is like a RISC-V based VM, which is much more powerful than things like the EVM, SVM, or any other kinds of existing VMs. And this is way too much to cover here, right? But I just want to clarify that this kind of step is not only just building new technology, but also evolving our existing technology stack. And so I think this should be a fundamental shift in thinking. Developers should just build applications. Users should just interact with applications. Blockchains are only needed to exist underneath the infrastructure to achieve consensus. And we've always talked about this. Blockchain is just infrastructure. People shouldn't be using blockchain. It should just exist as a part of a decentralized technology stack, right? So I really think that blockchains are dead and that we should long live Web3, right? Okay. So anyway, this is that preamble. If you want to quickly scan it, you can get access to this. And this will have a link to then my my shared security presentation. So I'll give this for 1 second. But again, putting in context here, what I'm about to show you is a deep dive into shared security. Basically, how we're able to achieve the multiple cores that we're going to use for that future. And this is meant to be a very kind of high-level introductory look into what shared security is and how we achieve this multi-core execution platform. And I want to clarify that this exact same framework is being used in that future technology stack. It is being used today to secure Polkadot, which helps with blockchain rollups, but it will also be used to help secure any kind of application using the same fundamental ideas of being able to support a multi-core blockchain system. Okay, so we'll jump into what is shared security. Actually, I'll take a pause. Is there any questions so far about what I just said? Hopefully not uncontroversial, but maybe something new, right? Okay, so let's go into this.
What about that jam computer? So
yeah.
AO hyperparallels coming out of testnet this month, and
okay.
So it's the same kind of thing, right?
No, I don't know about AO hypertestnet, but I know that jam is what you can think about it as an updated specification for a computer. So Polkadot right now, or let's start with this. Ethereum, I would say, is the first specification for a blockchain computer, right? Bitcoin is not a computer. Bitcoin is just a ledger. Ethereum legitimately is a computer because you can run applications on it. I would say Polkadot is an evolution of that idea, being able to create a multi-core computer. And Jam is yet another evolution of just making it more flexible and easy to use. So we have just designed basically a new type of computer, just like people have designed new chips. It's exactly that kind of idea.
So is it hyper-parallel then for like running Haskell and stuff?
It is hyper-parallel, not necessarily for running Haskell, but in terms of being able to run applications, it has over like 300 cores. And basically you can imagine running applications using one of those cores or multiple of the cores or applications sharing them. Anything you can imagine you can do with a multi-core processor, you can do with this. But it's not necessarily language specific. Okay. And actually, this presentation, the main takeaway I want from all of you is that you can understand how that multi-core architecture is designed using basically shared security. Okay, so what is shared security? Well, on the surface, shared security is an economic scaling solution for Web3 applications, right? But that's just the answer at the surface, right? It's kind of a bare bones answer. The topic itself goes much deeper, so I want to explore that and talk about why that's relevant. So what is security? That's, I think, the first starting point. So basically, every single blockchain in terms of security falls into two categories. You have technical security. That's things like cryptography, the languages you use, all that kind of stuff. And there's economic security. That's a combination of game theory and economics. And we will focus in this presentation on economic security. Like technical security, that's something that, obviously, if you use the right crypto, if you use the right algorithms, and use the right software, have the right tests, that will all achieve that. But what we really are talking about with shared security is a shared economic security. Economic security is represented by the economic cost to change the canonical history of a blockchain, right? So chains with more security are generally more resilient to malicious activity, like a double spend attack. So basically, an economic cost. So every single blockchain can be attacked. Bitcoin can be attacked. Other chains like Bitcoin Cash have shown exactly how it can be attacked. But the idea is that these attacks cost money. So if the amount of money it costs to attack the network is too high, then it won't make sense for any actor to actually attack the network. And that is what we're talking about here in terms of economic security. Now, I want to clarify that a double spend is not an attack. This is what we call an attack, a double spend attack. But this is actually the purpose of a blockchain. If I have $5 and I want to spend $5 to Alice and right away also spend $5 to Bob, obviously both of these transactions can't go through. I only have $5, right? So I can only spend to one of these two people. It is not an attack for me to make that transaction, those two transactions. It is actually up to the blockchain to decide which of these transactions are the valid one, right? Based on its whatever rules it has or how the network delays the propagation of the transaction. However, the whole point of the blockchain is to come to consensus which of these two transactions is valid, which of them is invalid, right? And so when we talk about double spend attack, we're talking about specifically trying to trick the blockchain to say that both of these transactions are valid, right? And what will that cost? So what does an attack look like? How can we actually attack a blockchain? So I'm sure you all heard of like Byzantine fault tolerance or this, 66% control type thing, right? Or 33% attackers. So imagine we have a blockchain which is split across the Asias and Africa, the Americas, and Australia. And you can see here there's 33 nodes in the Asia and Africa, 33 nodes in the Americas, and 34 malicious nodes in Australia. And in this situation, the cable which connects this part of the world with the Americas is cut. So the only way the world can contact each other is through Australia. And in this context, Australia is malicious, right? So Australia will use its power, basically the fragmentation in the network, to basically produce two different blockchains. So you can see here, these two sets of nodes comprise more than 66% of the nodes. So this blockchain is valid under that rule of this, the Byzantine fault tolerance. Similarly, this part of the network is also more than 66% because Australia has 34% total, and it's producing a different blockchain. And because Australia is malicious here, it is producing knowingly two different blockchain histories and saying that both of them are valid. Now, these different areas don't know better. They're basically following the rules of the BFT, and they're saying that this is okay. Now, eventually, we would hope that the internet lines would be connected back together, and we start to realize, well, hey, our blockchain doesn't match this other blockchain. And we notice, if we look at the history of the blocks, that Australia was the one who was actually double signing, right? They were basically equivocating on the rules of which blockchain they actually think is valid. Because they should have only ever said that one of those two blockchains was valid. And what happens eventually is that they find out this is okay, and then we will slash these nodes, right? So the cost of Australia doing this attack is how much money they will be slashed after the network figures out and unfragments itself, right? Now let's imagine that the slashing cost for Australia was, to say, $1 million, but in the time that they had control over the network, they were able to produce $1 billion of value. This is a great attack. This is a very valuable, profitable attack, and one that they will execute on. But for most secure systems, the cost of the attack is much, much higher than how much money or how much exploit you can actually take away from the network. But I want to clarify, this whole idea is supposed to put into your mind the fact that economics and security are ultimately tied together in blockchain systems. You need to be able to understand that the security of a network is directly tied to the economics of that network. And this can be a problem because bootstrapping is a huge problem for blockchains. So what is the bootstrapping problem? It is basically the problem describing where a new blockchain, which is brand new to the ecosystem, doesn't have a lot of reputation, doesn't have a lot of intrinsic value, is trying to get started, but it cannot provide any security because it doesn't have any value. And as we said, security and economics are tied together. So when you have a new chain, it usually has a small market cap. When you have a new chain, it's often very speculative. This is a disaster in terms of trying to create a secure system, a secure blockchain, right? So how do we solve this problem? Well, we use shared security. And that is the key idea and one of the key principles of what Polkadot was designed to do. Provide shared economic security to all the applications being built on top of it. So there's different forms of shared security today, and they've been evolving over time. We have native shared security. You might have heard of native rollups. This is, again, the idea that's kind of new. But this is what basically Polkadot has designed, a protocol-specific design for how we actually handle shared security. We've also had these kinds of other rollup ideas, other shared security ideas that have been designed after the fact. So optimistic and 0K rollups are all ideas of being able to use shared security for systems like Ethereum, but after the fact, where Ethereum is really just a general smart contract platform. We're going to try to build smart contracts to allow us to tap into the security of a bigger network like Ethereum. And then we also have restaking solutions to be able to basically not actually in the protocol handle proper rollups, but just be able to use other assets from other chains like Bitcoin and use that as a backing for providing security to a network. But I want to clarify that I don't think that these different kinds of shared security are equal. So let's look into Polkadot. I can describe to you our protocol, and then you can yourself look into the other shared security systems and see why they might be not as good. So what is Polkadot? So Polkadot really is a secure, scalable, resilient platform for Web3 applications and services. It is that platform for how you can build an application and inherit the properties of Web3. And as I mentioned already, we're really trying to design Polkadot to be the next evolution of the blockchain landscape, right? So if you can think about, again, Bitcoin as a calculator, Ethereum as a computer, Polkadot has really created a cloud server, a multi-core computer that can actually handle lots and lots of computation far beyond the standard computer you have in your home, right? And I think one of the really key visions that we want to have for Polkadot moving forward is that we want to do to Web3 what AWS did to Web2, right? AWS made cloud computing scalable, cheap, and easy to access, and we want to do the same thing for Web3 compute. For any kind of application they want to launch, we want to make it as easy, scalable, and cheap for people to launch those things onto Polkadot. And so Polkadot provides shared security. It is unique compared to most other networks in the fact that it provides all applications that run on Polkadot the same security guarantees as Polkadot itself, and that this is built in native to the protocol. It is not an afterthought. It is not something that's being bootstrapped on top of an existing protocol. We were always designing Polkadot to have shared security in mind. And so I want to go break down the building blocks of shared security, and you'll understand how this actually leads to this multi-core computer. So the building blocks of shared security is this execution meta protocol, the ideas of sequencing, availability, and approval. These are ideas that you should be very familiar with if you're in the rollup space, and the security hub settlement layer. So let's go one at a time. Execution meta protocol. So in the Polkadot ecosystem, each chain has their state transition function represented by a execution meta protocol. In this case, it's WASM. As I mentioned, we're moving forward towards a more RISC-V based system, but let's talk about WASM for now. That basically every single application built on Polkadot is represented by WASM. And WASM is really powerful because it is really easy to build applications into WASM. I hope I have a slide on this. Yeah, we can talk about this analogy. So you can imagine, for example, building to WASM is quite simple. As long as you have a language that can compile to it and you have very minimal requirements, you can design your application into a WASM blob. And you can think about these WASM blobs just like a game for a game console. So you can think about Polkadot as a game console. It has some kind of format or standard it understands, which is WASM. And as long as you build your game for that game console, you can then plug it in and you can use it and you can play the game you want. What Polkadot can actually do is even one step beyond that. It can actually run multiple applications at once across multiple cores, right? So it is able to take all these different WASM applications and run them just like, native, they are native blockchain on itself, right? They can actually fully verify and validate all of the state transitions of these blockchains. So in short, Polkadot really is a WASM executor, right? It is actually designed to be this general, I execute programs as long as they're in this format, right? And all of the applications in our ecosystem use that format for the state transition function. So really, this meta protocol allows Polkadot to execute any application in our ecosystem. It can run anything on the fly. And one of the important parts about that is that Polkadot itself, when you run a validator, it actually executes those other applications. It's not doing some kind of optimistic thing. It's not using a ZK rollup. It's not just assuming that things are running right. It actually executes those programs themselves, which is providing less trust and more truth. And as I mentioned, WASM is something that we are used today, but in the next generation of Polkadot, we'll be actually using PokaVM, which is a RISC-V based system, which will provide much more flexibility and power in terms of how applications are actually being executed. I don't go too much into this, but you can go to this link or this GitHub and learn a little bit more about PokaVM. I think there's also good YouTube videos on the PokaVM as well. Okay, now let's talk about multi-core execution. So now we have all applications running in some meta execution format. How are we going to actually execute a lot of things and actually scale things up? So in terms of blockchains, how we maximize scaling is a combination of two things. We want to be able to share our security as much as possible, right? We also want to be able to shard our execution as much as possible. How can we do the most things at once while sharing the security that we have across them? So this is what makes a really good protocol, and this is exactly what we've been optimizing for. So Polkadot, I would argue, is the first decentralized multi-core computer. And when I say multi-core, I really mean exactly what you know and you think about when you think about multiple cores, right? Your phone has multiple processing cores. Your laptop has multiple processing cores. This is how we scale to the next generation of computers. We allow multiple applications and processes to run in different threads in parallel and access the benefits of basically not having faster hardware, but more parallelized hardware. This is really how we scale up our hardware systems. And this allows for execution sharding. So if we can have a system with multiple execution cores, we can actually shard execution and execute things in parallel, right? And in Polkadot, all validators will execute all the blocks of Polkadot, but only a subset of those validators will actually execute a specific application or service. So this is how we shard execution. But again, everything is happening within Polkadot ecosystem, so all the security is being shared, right? But this actually is how Polkadot scales. We're not looking to make the fastest single core computer. We're looking to parallelize our tasks to be able to actually scale horizontally. So how do you validate a block? You need a block of transactions that you want to validate. You need the state that represents the transitions you want to make. So this is what we call a POV, a proof of validity. And I want to clarify that this is only a subset of the overall state of your blockchain. So imagine you have a transaction which is sending a transfer from Alice to Bob. But let's say your blockchain has 1 million users in it, right? You don't need all 1 million users to be in this proof. You only need Alice's balance and Bob's balance, and a proof that Alice and Bob's balance is inside the state root of the overall blockchain, right? So one thing I want to clarify here is that other blockchains, like Solana, for example, don't use a Merkle tree. They can never make this kind of proof. They can't. They're going to rely on other systems which are basically relying on more trust. But we can actually make these kinds of proofs. Ethereum can do the same, and we can actually prove only with data we need that this state transition, when executed in our state transition function, actually produces a new state which matches what we expect. So if Alice and Bob are doing a transfer, we only need that information. We run it into our, Bitcoin-based, blockchain or whatever kind of system we want, and we see the new balances of Alice and Bob. This is how we can validate a block. Now, given this property, let's look about how Polkadot actually scales out to validate multiple blocks, multiple applications at once. So you can imagine Polkadot basically taking in the blocks of transactions from many different applications, and they all submit the data I need. We already have in Polkadot the game console, the state transition function of those blockchains, and we have each application provide the block of transactions it wants to execute and its state that we need. We load all of that, and inside of Polkadot, we have a ton of validators, a ton of high-quality computers that will actually go and reprocess and validate these transactions, right? We can randomly assign each of these validators into a different application, and then have those validators report, was the application executing correctly? Was the final result what we expected, right? And basically, we can use that to then validate and secure the chain. So again, looking clearly into here, we have just shown how we can take a existing validator set, which is all under one security umbrella, all under one economic security umbrella, which is like the DOT token and staking, and we can actually split them up to parallelize the work across multiple different applications. And if we do this randomly, and we have a good VRF, we are able to basically, in a decentralized way, execute and process multiple applications at once. So how do we stop things from going wrong? There's other processes and meta protocols which handle if there were disputes, right? We shouldn't assume that everything comes to consensus immediately. So we have things like data availability, which allows for all the data necessary to validate things themselves to be made available. So anyone can validate this work. We have approval checking, which allows other nodes to basically verify that the other tasks being done by other nodes are doing correctly. And dispute handling, that in the situation where two nodes or two validators are saying, hey, we don't agree on the output, that we actually escalate the process to more and more validators, so eventually we get a consensus over the whole network, right? But assuming, again, these things don't happen very often, that this is kind of the default case and things just work, this scales really, really well. And in many ways, you can think about Polkadot like this. In the best case scenario, Polkadot is a very high throughput parallelized computer. In the worst case scenario, Polkadot kind of reverts back to a single blockchain and everyone executes everything and we still get a final consensus. This is really, really powerful. Okay, so now you kind of understand how we do this multi-core execution. The last piece of the puzzle is the relay chain. We need a relay chain. We need a settlement layer for Polkadot to work. So you can think about the relay chain as a security hub for Polkadot, right? The relay chain is basically the anchor for the Polkadot cloud. It provides a base economic utility token, which is DOT. It provides a high-quality group of validators, which we talked about already. It stores essential data needed for each of the different blockchains, like the state transition function and any kinds of Merkle root state or anything like that. And it finally establishes finality for the application state. It actually determines which outcome is the correct outcome and the one that you can actually use to do the basis of how you interact with the real world. What is actually final? So each of these different slices here represents a block on Polkadot. And each of these different colors represents some kind of state transition for an application running on Polkadot. So you can see here, as each of these slices on Polkadot get finalized, all of the applications and their state transitions also get finalized, right? So basically, Polkadot provides a canonical state for every application in the ecosystem. But more than that, because every single slice has all the applications being finalized all together. That also means interactions between applications also get finalized. This is a really, really important piece of a native shared security and native interoperability, that we're actually able to secure the interactions between two applications and how they work. So if, for example, one application A and B, they make some assumption about the state of these two applications, if we finalize that, that interaction is also finalized. It's impossible that this interaction would happen and this one would get rolled back, because all of the things are happening together in these finalized slices, right? So this actually leads to also, not only shared security helping the applications get more secure individually, but also get more secure in the way they interact with each other. So again, going back to the building blocks of shared security, we have the execution meta protocol, we have sequencing, availability, and approval, and finally the security hub, the settlement layer. And this is what Polkadot has designed. It's designed right now WASM, this multi-core protocol, and the relay chain. It provides all the building blocks of shared security. And I would argue that other ecosystems, other protocols do not necessarily provide all these different pieces. And as a result, I think those protocols are not going to be as good in terms of shared security or in terms of scaling blockchains. So do I still have time? I think I have a little bit of time left, right? Yeah. Okay. So I'm going to compare some different options across the different ideas and give you something to think about. They all have pros and cons. I want to clarify there's no one right answer to anything, right? So it's all about you to think about and identify for yourself what you think is good. So when we look at restaking solutions, what's nice about them is that they are protocol agnostic. Basically, any blockchain can be used in a restaking solution, because all you're doing is basically using the economic value of a token and using it as a backing for how you want to secure a new blockchain, right? So smaller and newer chains can rely on more valuable economies like ETH or Bitcoin or whatever as a restaking solution. Now, the problem with restaking is that as tokens are continually restaked, the economic cost to attack the chain secured by those tokens decreases. For example, imagine I have a chain and Bitcoin is the only one securing that chain, right? So if you're going to attack that chain, you're going to get slashed some amount of Bitcoin, right? But let's say I use that exact same Bitcoin and I restake that Bitcoin across 5 networks. Now if I can create an attack which attacks all 5 networks, right, only one set of Bitcoin is going to get slashed. So basically the cost to attack all those networks have gone down because I've manufactured a way to basically reuse the same security twice. This is not great. And this is actually why, if you look at Vitalik's blog post, he really doesn't like a lot of the restaking solutions on Ethereum. Because Ethereum being constantly restaked across many networks not only hurts those network security, but also hurts the security of Ethereum itself, right? Because those tokens are often being used for staking against ETH, but also being re-put into DeFi protocols or other staking solutions, right? And a lot of these restaking solutions, because they're not actually at the protocol level, because they're not actually built at a computer level to actually handle fraud, a lot of this stuff comes back to centralized sources of trust. So a lot of these restaking solutions are dependent on like multi-sigs. And this is really not what we're designing. It's not really Web3, right? Okay, let's look at optimistic rollups. So optimistic rollups are really cool because they are not limited by the complexity of the on-chain VM, right? So basically optimistic rollups where you make the assumption that this block is valid and you give some time for anyone to argue this block is invalid with some kind of proof, and there's a dispute period, and then that basically happens. But what's nice about that is basically what you put on the chain is only the results of the execution. You don't have to actually execute anything itself, right? And this can be very highly parallelized, and you can put a lot of data, and you can do a lot of basic execution in optimistic rollups, which never really hits the main network. Now, the problem with optimistic rollups is that there's a lot of concerns around centralization and censorship of sequencers, right? Sequencers basically in most optimistic rollups, like Optimism, stuff like that, have not achieved the full decentralization needed to be able to feel like the whole system itself is decentralized. So even if you're rolling up onto Ethereum, which is very decentralized, the sequencers themselves, if they're not decentralized, can censor transactions, can adjust the order of blocks, can make things in ways that aren't very, very good, right? The other thing is that there's a long time to finality. So this could be days. I think it's like 7 days for Optimism. This is basically because you need that dispute period. Because we're not actually re-executing anything, you need 7 days for anyone to be able to say, hey, this is actually not valid. Because if we have a short dispute period, let's say like 1 hour, 2 hours, it becomes very easy for an attacker to basically block the network or block any kind of signals for those 1-2 hours to get away with a big transaction. And if something gets finalized, which shouldn't be finalized, that's really bad for everybody, right? And then, of course, settlement layers can be attacked. So one of the problems with optimistic rollups is that I have a chain which is dependent on optimistic rollup, and that chain is not designed for handling rollups natively, right? Let's say it's a smart contract platform. And let's say that in that week where something really important is happening, there's a new NFT drop for new kitties or zombies or whatever meme you want to have. That network gets congested, and that congestion affects your rollup, affects the ability for you to actually insert your blockchain and get it finalized. And we had problems like this where literally on Ethereum there was a time where an NFT drop happened, transaction volumes spiked, prices spiked, and the optimistic rollup protocol didn't have enough money to spend to validate this next transaction, which basically stalled that network, which was really, really bad, right? So these are a lot of the same problems that we suffer for basically any kind of non-native rollup system. Okay, zero-knowledge rollups. This is very similar to optimistic rollups, but they actually use a new kind of mathematical magic to basically prove that things are correct. So unlike optimistic rollups, where you have this dispute period, zero-knowledge rollups, they take a really hard problem, make it into a much easier to verify problem, which can actually be executed in a smart contract. And as long as that is correct, you can basically say everything there is valid. It is instant finality, truly instant finality, right? But the problem here is that there's, again, concerns around centralization of sequencers and provers. So for you to be able to take a really complex problem and turn it into a simple ZK proof, you need very high-powered computers, which are not really accessible by most people. And most of these ZK systems are dependent on centralized sequencers to be able to create those ZK proofs. And also, I mean, this is being improved a lot as of recently, so this might be a bullet point I have to remove in maybe 1 or 2 years. But ZK circuits are kind of hard to build right now. There are a lot of VMs which are trying to create ZK circuits which map the EVM, but if they're only like 98% compatible, right? They don't have all of the different opcodes and stuff in there. And it's really challenging. This is something that is constantly needing to be improved. But I do actually believe that in the long term, this will be a bullet point that won't even be worth mentioning. But what we'll be mentioning is that if you use a ZK rollup on a non-native rollup blockchain, you will still have all the same problems described before, where if that blockchain itself is pushing through transactions and other spam that's going through it, your ZK rollup may suffer from not being able to just submit a transaction, not be able to pay for the transaction fees, not be able to fit into a block. And that can affect your uptime. That can affect your finality time. And finally, native rollups, right? This is, again, the idea that as of January this year, Ethereum is looking towards. So what does a native rollup provide? Why is it good? Well, it's very important that native rollups is a protocol level handling of shared security, interoperability, and execution. So Polkadot does handle other kinds of transactions like transfers, soon be smart contracts, all that kind of stuff. But a native rollup says we prioritize securing other chains as #1 priority. We have allocated block space for just doing securing of other blockchains so that transactions on the blockchain will not affect other rollups. So we will never suffer on Polkadot a problem where one chain will not get its chain validated or finalized. It will always be able to have room because we have put in the native protocol the ability for that blockchain to secure the other chains. And it's really easy to develop STF. Again, anything that builds to WASM and soon RISC-V will be able to work on this native rollup system. It has incredible time to finality. It's usually under 30 seconds, so it's not as fast as a ZK instant finality, but much, much better than the 7 days or whatever for optimistic finality. And 30 seconds is often pretty good for most systems out there, right? We provide in our native protocol native data availability. So this is another problem that we have. So people who are trying to build rollups in Ethereum space often have to rely on other systems like Celestia or EigenDA or whatever else to provide DA needed for the rollups to work. Because Polkadot had in mind building the system natively, we have provided already these systems in Polkadot itself, right? And there's much less concern over centralization of collators and sequencers. Now, what are the problems? What are the problems with native rollups? Well, the biggest problem with native rollups is that there's a lot of limitations required to be able to keep our application compatible with the Polkadot system. For example, if you have a blockchain which is reliant on some kind of GPU acceleration, right? In order for it to work in the protocol I described, all the different validators in Polkadot need to also have GPU acceleration, need to all have GPUs, right? So whatever kind of assumption you make about like hardware or certain chips or certain quantum stuff or certain GPU stuff, all of that must happen across the whole network. Otherwise, Polkadot can't secure the chain. It can't actually revalidate the algorithm, right? And again, this is actually a bullet point I can remove because we're going to move to RISC-V. And RISC-V, as I understand, is basically native speed. We've been able to achieve almost native speed execution using RISC-V on this native rollup system. And the last problem I would say is that there's a lot of data being provided and made for that POV. So as I mentioned, in order to do the actual re-execution, you need to have that slice of data, which is all the information needed for the state transition function to actually execute, right? This is a lot of data when compared to things like ZK proofs and compared to optimistic proofs, right? But thankfully, because our data availability provided by Polkadot is native, it's actually quite large, and we have the highest data availability bandwidth of any blockchain out there. I think we're like 42 megabytes per second, and the next best one is like, Celestia at like 8 megabytes or 1 megabyte? I don't remember right now, but nothing even close to what Polkadot can do. So, but there are real downsides to this system, right? But I think these upsides far outweigh the downsides. So yeah, that's basically the high-level idea. If you can understand how this presentation came across, if you can understand how we actually designed shared security and how we were able to create multiple execution cores, you can understand the basis of which Polkadot scales and why shared security is super important. So thank you, and I'm here to take any questions. Yeah. Anything? Nothing? Okay, well, I'm going to be around. Yep, one in the back. Yeah. Can we? I'm going to toss to you, and you're going to toss back there. Okay. There's no stupid questions. There's nothing stupid.
Yeah, so you said a 30-second finality.
Yeah.
Let's say someone wants to... Oh, it's a mic, actually. Okay. Let's say someone wants to build an extremely fast application that needs milliseconds
Yes.
sort of finality. Do you think there is a way to actually build that in Polkadot, as you described?
There is a way to so Polkadot already is designing, and it has a prototype for blockchain being built blocks being run every 0.5 seconds, right? But the finality time is still around 30 seconds. So we can't solve the finality problem. And again, I would kind of argue a basic idea here. Imagine you have a decentralized computing system with computers all around the world. How is it possible that all these computers can come to an agreement in a millisecond? There's no internet fast enough. There's no computer fast enough for that to happen. So if we actually talk about in a real world how real systems should actually validate, 30 seconds probably could be improved with better internet speeds and faster computers, but it's never going to get to that kind of level of speed. Now what we can do is what we can actually allow you to do is make a blockchain which itself produces blocks every 0.5 seconds, and then we bundle a bunch of those blocks together and submit it to the network as one bigger block, right? So you still get basically a state transition function where you know every 0.5 seconds what you're building on top of, right? Like if you're doing gaming, what the last position of the user was, you can do that. But you won't ever be able to achieve finality at like 0.1 millisecond. And actually no blockchain out there does that. Even ZK rollups, I mentioned instant finality. So literally as soon as the transaction gets into the block, it's finalized. But in order to create that ZK proof, it requires lots of time, right? So if you count that as part of the finality, like how long from my transaction being submitted to it being included in the block and finalized, 30 seconds is still actually quite fast, right? Yeah.
Hello. Just a question around kind of ZK rollups a little bit.
Yeah.
So, I know the complexity of the proofs are, it's pretty immense, take a lot of compute power. That's why I think there's a lot of centralization in sequencers.
Yes.
Do you imagine that improving over time so that, they can actually provide kind of higher throughput systems? Because right now I believe they're pretty limited.
I absolutely think that they will improve. I think that I think ZK. I'm very bullish on ZK. I think that Polkadot is already looking into using more ZK, and it's possible that a lot of what we do with re-execution could be transitioned to ZK in the future. Like what I described to you, for example, here we kind of use WASM and we say we re-execute everything. Instead of WASM, it could be a ZK proof, and we just finalize it. But the problem is that I think today, ZK does not meet the bar that we need for building a resilient system. So I think that we want to keep our eye on it. We have researchers looking into this stuff. We actually use parts of ZK in parts of Polkadot, which are not this main protocol. Yeah, I think it will happen. But I think, as I understand, the ZK stuff will really be improved with some dedicated hardware. So that would also be a concern if dedicated hardware becomes a centralization risk, But I mean, practically speaking, everyone uses chips made all in Taiwan anyway, right? So, it's a much bigger problem, right? But I do think, I am very bullish on ZK. I do not know the timeline. It's very hard to say 5 years, 10 years, or what, right? Mike again? Yeah.
So Polkadot is moving forward to this Polkadot cloud, and how far away do you see in the future? I mean, we will have like services in Jam and all of this stuff. So how far away in the future you think that regular developers will be able to, like, I don't know, upload like a Docker container and be executed in like Polkadot cloud or something like that?
Yeah, it's hard to say. I don't think this will be something that it won't be like a leap. It'll be so, step by step. So I think that today you can already run basically blockchain applications on Polkadot. We are looking into unlocking different resources in Polkadot, like data availability or the execution, to other kinds of applications and other kinds of frameworks to be able to use that. And then eventually we're going to have Jam, which is going to change, what kind of application you can run, how long it can run for, all that kind of stuff. I think it'll be very stepping stone. How long until a Docker container could just be uploaded and run? I don't think it's going to happen in the next 3 years. But I think that it could happen in the next 5 to 10. I mean, I'm just making up numbers at this point, right? Development is hard. But I do think once these ideas start picking up and getting momentum, it'll just be more and more obvious. I think what it's really changed for me in the last year has been a strong understanding that blockchain is just designed for a decentralized computer. And if we start with that, all the things and all the evolution for computers that we've seen over the last 10 years, we will basically see emulated or repeated in the blockchain space. So think about how, when I was first building computers, I had a 1-core, 4 gigahertz processor. Now I have MacBooks, which are much faster than that, all running on like 1.8 gigahertz, right? It's much smaller, but having many, many cores, right? Ethereum or Solana exists as this like super high-speed 1-core processor. I think Polkadot is trying to show, hey, we can actually build a multi-core system which can scale much faster and with more throughput than that, right? I think once applications are starting to be designed for multi-core systems, like, the transition from the single core to multi-core system, having applications actually handle multiple threads was not something that happened overnight. But once it did happen, it made applications much more high throughput. And even things like, for example, the evolution that now the current Apple Silicon not only has multiple cores, but some are efficiency cores and some are high performance cores. I think these are ideas we have not built in Polkadot yet, but will be emulated again in the blockchain space. And that will again bring more efficiency. Like there'll be cores for just basic transactions and then cores for contracts, and the assumptions on those cores and the design of those cores might be different, right? These are all things I expect a very natural parallel to evolution to happen. So my question to you might be like, okay, well, if we just invented the multi-core processor, how many years was it from then that Docker actually got to a really usable spot? That might be a good mapping, right? Yeah. Any other questions?
So you talked about two things quite briefly, one of which was the relay chain, and
Yep.
then the other was Jam.
Yep.
Now, as I understand it, when Jam comes online and it actually, the Jam chain replaces the relay chain.
Yes.
And I know we're preparing for that at the moment by switching functionalities to Asset Hub. But when the moment comes to actually replace that relay chain with the Jam chain, what does that look like practically? And is there going to be downtime? Is there going to be just going to slide in smoothly?
What they want to clarify is I think that relay chain is an idea right now. Jam chain is an idea in the future. They're both just versions of this security hub settlement layer. So in terms of how it maps into the design of a system, it's basically the same thing. Now, in terms of the implementation detail, like how it actually executes, I'm pretty sure that moving to Jam chain will be a hard fork. It'll be like legitimately that we pause all of Polkadot. Polkadot might even go down for a day or whatever, like, or some kind of state of it that we pause it, and we have to basically re-genesis Polkadot onto Jam chain. But in terms of like its purpose, the relay chain and the Jam chain will be basically the same thing as a settlement layer and a security hub for the overall network, for the cloud. But it'll be a regenesis. I mean, how exactly that happens, I have no idea. It's gonna, but I mean, these kinds of forks, they do happen. For example, Ethereum, I think one of the most impressive things I've seen in the decentralized space is that Ethereum transitioned to proof of work, to proof of stake, and it did so in a pretty decentralized, pretty hiccup-free way. I think that these things are possible with the right amount of conviction and agreement on what we want to see in the future. Okay, I think that's my time. One last question. Okay, sure. You have 2 minutes until it hits 3 o'clock.
So we're in the Blockspace mansion, so I was wondering if you could comment about the role of Blockspace in this, what do you call it, the future cloud computer?
Yeah. I mean, I have another presentation that's even better for all that kind of stuff, but it really hits on Blockspace. Let me see, future. This will be a presentation I'll be giving here in Denver. So if you can catch my talk tomorrow, I think it's like 3 o'clock, something like that. But I say here that Blockspace, yeah, the resource of Web3 is Blockspace. I mean, even the idea of having blockchains or anything is just, I almost think of it as obsolete. Like, we're all here, the whole ecosystem's like, we're trying to build blockchains, I have the new blockchain, I'm building a new L2 blockchain. It's not that at all. We all should be building applications. And we want applications to have properties of Web3. We want an application that is resilient. We want an application that is decentralized. We want an application that is verifiable. Now, it happens that a blockchain has these properties, but this is just one piece of building an overall application. If instead we can provide a resource to application, like cloud computers provide resources to basically run your applications on them. If we can provide a resource which has these properties of Web3, then you don't need to build a blockchain. You just need to build an application. And Blockspace is that resource. Blockspace is basically the evolution of taking a blockchain and actually exposing these resources, these raw resources, to application developers and allow them to use it without ever having to think about building a blockchain, right? And so I think this is really the move forward. Blockspace, I think people will forget where the word block comes from in Blockspace, just like people forget why the save icon's a floppy disk, right? Like, eventually, the idea of a blockchain will be so infrastructure, will be so deep, will be so forgotten about. It will just be the fact that I built an application with these Web3 properties, right? These properties which are super, super important, right? This is what I want. Blockchain is a tool to get you there. It's not everything, but we have been basically limited today by not creating systems which are flexible enough to expose these properties to you without you having to build a blockchain yourself. And again, the idea with the cloud, the idea of what we're trying to build is to abstract that away from you. That you just build an app, you run it on a platform, you get these properties. So Blockspace will be the shift in terms of how you access those resources. Is that a good answer?
I don't know yet.
Okay, we'll see. We'll find out, I guess. Okay. Well, thank you, everyone.